So, and the main thing you need to know is there is a reference. So I'll mostly, actually my favorite reference is the Dennis Gatesbury text called Outline of Proof of Geometric Lengths, and then there are some other words there. So, and so we are talking about local systems, which corresponds to the outline. In the outline text, it would be sections 8.2 and 4.1 and 4.3. And let me say that the reason I like this text is because, first of all, it has the same style as the talks in this conference, so the general point of view is like this, but also it's sufficiently informal that you can get the general idea and then look at something more special, like the whole sequence of papers, if you choose to do so. Okay, and so my conventions will be very similar to what happened in the previous talk. So I'll work over an algebraically closed field of characteristic 0, which are probably denoted by C. And so I'm going to fix a smooth projective curve. And a reductive group. And secretly, for the purposes of this talk, G is not supposed to be the same as G in the last talk. It's supposed to be the Lenzman's dual of it, but we won't see any of this. So, since this talk is entirely on one side of the story, I'll just denote it by G and let the next speaker deal with it. So, okay, and so now I can fulfill my main objective and just let's make this into definition. So that I'll denote by LocSys. I mean, sometimes people just write LS. I don't know if some of the speakers use this. I hope you won't be confused. So these are maybe in the opposite order, makes no sense. So this is going to be the moduli stack of G local systems on X. And I'm going to fill in the details of the definition. So first of all, when I say local systems, this can mean many different things. So technically, what I consider would be called the RAM local system. And so what this, and there are two, I guess, or at least as I see, there are two ways of thinking about the RAM local systems. There is maybe a more classical approach where you think of a local system as a bundle with an integrable connection. So let's talk a little bit about this. So first point of view. So we are local system is going to be a G bundle with an integrable line somewhere, integrable connection. So, for example, if G is GLN, then I'm going to look at pairs E nabla, where E is a rank N vector bundle on my curve X, and nabla is a connection in the classical sense, so it's a C-linear map which tells us how to differentiate sections of our bundle. I'm not really distinguishing between a vector bundle and the locally free sheaf of its sections. I hope nobody minds. So this is C linear and it's satisfying the alignments. Now blah F times S is F now blah S plus S divided by F. And technically, I mean, I guess I planned to put integrable, but it's not an integrable connection thing. And the reason I put integrable in connection in parentheses is because technically you have to add an extra condition about how nabla acts in different directions, but because X is one-dimensional, this is automatic in this case. So for example, for GLM, the definition works as written on the board. Okay. So, I mean, there are some nice things to be said about this definition. For example, it nicely ties with the discussion of the stack of G bundles. So you see that in particular, if you have a connection, if you have a bundle with connection, you forget a connection, you just get a bundle. So there is going to be a picture of this will be the totality of G bundles, and then so these are just pairs. I mean, let's for this picture, let me continue using this notation from the GLN case. So there will be just individual vector bundles upstairs, and then I can choose I can make an extra choice of a connection and get a point of this space of local systems. And moreover, what else can I see from here? I can see that if it's not hard to see that if a vector bundle is fixed, then connections on a fixed vector bundle will form an affine space. So for fixed E, nablas form an affine space if nablas exist. So over a single point, we will have an affine space of connections. So this, and I'm kind of tempted to say that the space of local systems forms an affine bundle over the space of bundles, but you should keep in mind that the map is not surjective. Not every bundle admits a connection. So there is some subspace, which is the image from upstairs, and then there are some bundles that do not have any connection. Is the subspace open? The subspace is open. Okay. So, any other questions? Let me, before we move on to the second approach, let me maybe let me say some things that maybe are easier or they can be approached classically. So, what are some of the properties of this space of local systems? First of all, I keep calling it space, which because I didn't make any precise statements yet, but the actual properties would be that so it's a step. It's an algebraic step of finite type And generally speaking, it won't be a classical algebraic stack, so it's an object of derived algebraic geometry. So let me put derived. And as a derived object, it's quasi-smooth. Which is, again, in the derived algebraic geometry, it's a counterpart of being local complete intersection. Derived local complete intersection. Local. So let me try to kind of summarize this, especially if you haven't seen this kind of if you haven't seen this kind of object before. I mean, let me try to suggest how one can think about this. Now, first of all, we have a map from LocSys to Bun-G, and this map is there is nothing sticky about this map. This map, like, we can say that in relative terms, LocSys is a scheme over Bun-G. Like, over each point, we just have a vector space. There are no fancy notion of automorphisms if the bundle is fixed. Okay, good. So this means that in some ways, we can understand the geometry of this stack by comparing it to Bun-G. Now, we know from the previous talk that Bun-G is nice, well, in some ways, and not so nice in some other ways. For example, one weird thing about it is that it's not quasi-compact. So it somehow goes off. It might have infinitely many components, for example, for GM, but if the group is non-abelian, it's somehow like there is some kind of going off to infinity. So now, despite this, when I said that the stack of local systems is of finite type, that in particular means it is quasi-compact. So the first point is that this, if you go far off, if you go far away, then this on the stack of G bundles, then these G bundles lose the ability to support a connection. So, or you can say like G bundles that are very unstable do not have a connection. So this part actually can be, so to say, covered by a single chunk. So that explains, that's my first point. That explains the finite type thing. So now the price we pay for it, if you like, is that this local complete intersection, derived local complete intersection thing, which is a weaker substitute of smoothness of Bun-G. So remember, the stack of G bundles is smooth. This guy is not. That's the main, that's, I guess, the next point. However, it is, it can be cut out by, or at least locally, it can be cut out by equations within something. And at least conceptually, the reason why it's, so let me maybe make two more remarks and move on. So first remark is that the reason why is LocSys only quasi-smooth? Why does it fail to be smooth while Bun-G, I don't know why I put G for one, not the other, there's no secret meaning there. So Bun-G, it's somehow I think it's the reason of it. It's like LocSys Bun-G. And so Bun-G is smooth. And the answer is that the reason Bun-G is smooth is because the reason the stack of G bundles is smooth is because of basically of deformation theory, because its tangent space is controlled by the cohomology of certain vector bundle. on X. So smooth. This is because the homology of X with coefficients in a vector bundle sit in degrees 1 and below. So like h greater than 1 is equal to 0. Now let's say h I is equal to 0 for I plus 1. But when we work with local systems, the corresponding the calculation of the tangent space will produce the Ramka homology. So, and if you haven't seen this calculation, it's a nice exercise in deformation theory. So it will produce the Ramka homology with coefficients in a local system. And for the Ramka homology, the estimate will go one step further. So now cohomology can occur in degrees up to 2, and that exactly allows our stack, or this is the mechanism by which the stack fails to be smooth, but still can be local complete intersection. Okay, I hope this made sense. Yes.
From what I said, I thought this is an affine bundle of its image. It should be smooth, and then
it's not. The problem is that the dimension is not constant. So it's an affine bundle. Like in a certain sense, it's not just an affine bundle. It's actually an affine bundle corresponding to the cotangent bundle to band G. Now, the problem is that because band G is a stack and not a space, its cotangent bundle is not really a vector bundle, it's a short complex. And this means that its cohomology are allowed to jump. So, like, I mean, let's say this, which cotangent bundle, which affine bundle, like in this example. So if I have two connections like this and I take their difference, then the difference, this extra differential term will cancel out, and the difference will just be a linear map, which would be what's called a Higgs field. So so form an affine space, namely it's the affine space, let's say, over. I mean, in the case of GLN, I'll just write H0 of X E endomorphisms of E over omega. For arbitrary group, you have to write the twisted form of the Lie algebra instead, but that's the general shape. So the point is that as your vector bundle varies, this thing will vary, and the only thing you have will be semi-continuity. So this dimension of H0 will jump, so it's not a vector bundle in the classical sense. It's more like the total space of a coherent sheet. Yes.
Yeah, here, where they said it's literally the total space of the coherent complex or coherent sheet of 1G. The LocSys G.
No,
No,
it's not. It would be if we had this. So it's the twisted version. It's a twisted version of the cotangent space to band G. And so, if you like, you can ask a general question. Suppose you have a smooth stack. What does its cotangent complex or what does its cotangent stack or a twisted cotangent stack look like? And you will see that this quasi-smoothness condition appears very naturally, and classically it appears because of the Hamiltonian reduction procedure. You need to take the zero locus of some map, and that's the thing. Yes?
can we assume in your second talk you will talk more about quasi-students.
I was hoping to, which is why I was mostly hoping to avoid this conversation now. But it's also the fun.
I'm saying if you didn't understand, you don't know what quasi-students is, don't worry. Dima will explain it in
Right.
the calculations.
Well, I also feel like there are basically two parts. My talk is called Talk About Local Systems, and then this references, this is about local systems, this is about RAM space. So I feel like I have to talk about local systems for at least a significant portion of the talk before I jump to the second.
Does the whole R gamma of X with values also show up if you think of it as like a derived sample function?
So our gamma of X, you mean H?
Yeah.
Well, H1 of that is like the abstraction, so yeah. I mean, let me, before we say goodbye to this, let me actually draw a cartoon, which is also a nice calculation. So, and it ties back to the talk with the previous one. So let's consider a very, I'll make it as let's say, what I consider this first non-trivial case where the group is GL2 and let X be Q. So then we already had a picture, some kind of picture of bun G. So I'm allowed to use this. So there is O squared, which degenerates into O1 plus O minus 1, which degenerates into O2 plus O minus 2, and you can see where this is. So, but in fact, the reason I chose GL2 is so that not all vector bundles have degree 0. Now I also have O plus O minus 1 degenerated into O1 plus O minus 2, and so on. And O plus O1, blah, blah, blah. Anyway, so I have this whole zoo of points really. They're the points of the stack bun T. And there are so many, that's what makes it non-quasi-compact. If I truncate, like if I, for example, truncate at any point, this will be quasi. Now, I mean, now we should ask which of these vector bundles admit an integrable connection. And which is, by the way, a good question in general, and there is a neat answer that I'm not going to explore. But in this particular case, the answer is that this thing, that one is the trivial bundle is the only thing that admits a connection, which secretly, I mean, I guess if you want to cheat, you can explain it by saying that this is due to P1 being simply connected. P1 is simply connected, the only bundle with connection on it is the trivial bundle, and the line vector bundle is trivial. So, so all that stuff, all these extra components, all these more and more unstable things don't affect our stack of G bundles. We only need to know the trivial. Now, okay, so what are connections on the trivial? So, what are connections on well, I mean, it's a trivial vector bundle, so I can write the connection in a very classical way. A1x, A2x. So dx, where I guess I'm thinking of these expressions as polynomials. So if I just ask them to be polynomials, this will guarantee that I have a connection on A1, and I'll also have to ask for this connection to have no pole at infinity. So I have to write an expression like this and ask that under the coordinate range x goes to 1 over xi, there is still no pole. And the fact is that because of the way, because of all the rules I learned in calculus courses, when I have a connection, when I have a polynomial, let's say this A11 of X, which is, it has some coefficients. I don't need X anymore. So I have, I don't know why this is. So I have a polynomial and I change this differential form to dxi. I will get something like minus a line 1d over psi to the power e plus 2. So basically dx, because of this, dx is going to be minus dxi over psi squared. So all of these coefficients will appear, but they will appear with a shift. Meaning there will be an empty spot. So there will be an empty spot with coefficients psi. And so with the coefficient of 1 over xi. And now I'm supposed to ask for this connection to have no pole, so I'm supposed to set all of this equal to 0. So I set all of this 1 by 1 equal to 0, and then, but that's not it. At the end, I also have to write the equation 0 equals 0. So I have, if you like, I have a set of equations that cuts out my my space of connections, but some of these equations are redundant. Some of these equations are of the form 0 equals 0, and that's exactly how derived structure appears. So answer that I'm trying to justify by this informal calculation is that that's the stack of G local systems on P1, where in my case G is GL2, but the calculate this argument is actually general, looks something like this. It's a point, it's a fiber product of point with a point over a vector space, which is the Lie algebra, mod out by G. So if you ignore all the GG structure, if you ignore all the derived structure, you just see the classifying stack of a point. But it's there, and you should think about it being there classically coming from unnecessary redundant equations. Okay, I'm ready to move on. All right, so this was all the first point of view, but I strongly suggest that we actually focus on the second approach. And the second approach thinks about connections as living not on X, but on the Durand stack of X. So LocSys. So let me make this particle. So local systems are G bundles on Durand, where this is one of those definitions that's very easy to write down, but it's not, I mean, that it takes a long time to digest. So let me at least formally write a set of definitions. So first we define X Durand. So this is something defined by its as usual by its S points. So which are going to be maps from the underlying reduced subscheme of S to X. And well, I guess I can. And the stack of local systems is going to be defined similarly to the stack of G bundles, but with this sub-index that sort of changes everything. So what is this? Of S will be maps S plus so, well, I mean, logically, I wrote everything, like basically the entire content of on the first part of the talk. Now, I don't know. Does it make sense? Probably it does. Okay, that's good. So let's just say, so, I mean, again, this is one of those things, again, that are kind of hard to really explain. You have to think about it. But let me say just a couple of words here. So what's going on here? So this definition somehow formalizes the idea of parallel transform. So formalize parallel transport. So this so the idea is that if you have an integrable connection of an object and you know it at a point, you also know it on an infinitesimal neighborhood. This is why. This is why when we define this the run stack as this, we say that so if you're trying to test, so if you have your X and you want to define something that has a connection on it, then you don't need to test. So when you're trying to test it by maps from a scheme to X, you only need to know what this map does to the reduced part of S, because the connection will allow you to expand from the to parallel transport, maybe using this language, from the reduced part of S to the non-reduced part. So I don't know. I'm kind of tempted to move on. I'll leave this at this cryptic place. So unless somebody asks it, yes.
Okay, yeah. This is defined at this bunker on animated rings.
Whatever your framework is. At this point, I don't even like this definition in a way predates. I mean, this in not quite in this form, but in the form very close to this. This goes back to GraphND. So this you don't even have to work. This is about connections. This is not about the derived store. So you can completely like separate the two hemispheres of your brain and like completely forget about all the derived story and use this definition classically.
But I meant for the third one, for LocSys.
No, but even like you can use this classically, but then of course you won't see any of the derived story. Now, also, now if you want to work classically, I mean, honestly, I work in characteristics here, right? So I don't mind just going to commutative DG rings. Commutative DG algebras over CR. But if you prefer, I mean, there are different, I mean, it's more of a framework, and then you should feel free to substitute the particular set of conventions that you are most comfortable.
Dima, I think the question is, do you get the right derived stack? You get the correct derived stack if you take this formula as defined on derived reference you want. The answer is yes.
Well,
Right? Is that the question, Mikhail?
Yes.
okay. Fine. Yes.
Can you say about why LocSys is finite?
So I mean, the main thing is that it's a the surprising thing is that it's a finite type as opposed to local, and that's this quasi-smooth, quasi-compactness. So it's a finite type because that thing is quasi-compact in LocSys, and so I mean, again, there is a classical question of which G bundles admit connection, and so so basically but for purposes of this thing, you just need to show that if a G bundle is very unstable, or if it's not in the correct connected component, then it doesn't.
Yes, can you draw the one around?
Kind of. I mean, somehow the the main idea is that this is like P1 with infinitesimally close points identified. So somehow I have to draw P1, and then like if I identify these 2 points, I'll get the cusp. If I identify even closer, so somehow I have P1, but every point is only defined up to infinitesimal. There is something quantum about it, right? So instead of points being in a fixed position, there is like this, I don't know, this cloud of points which are all indistinguishable from each other. So yeah, maybe that's a good way to phrase it. Like it's P1 with infinitesimally close points being indistinguished. And the idea is that a vector bundle on such a thing, so a vector bundle on such a thing is the same as a bundle with connection. A G bundle on such a thing is the same as a G bundle with connection. A quasi-coherent sheaf on such a thing is the same as a D module. So.
Can I ask one more question? So in the answer that you explained for LocSys of G on P1, does one also get that by decomposing P1 into A1, A1, and GM? And will that
I think that's almost how I got it. Yes. I mean, or we can follow more like the last one thing and think about it as P1 as A1 and then the formal discrete infinity.
And I mean, also you can think about it in terms of the also you said earlier, where it's mapping to sort of 1G, which is basically DG here, and then fibers are sort of like R gamma of endomorphism from G tensor omega, which turns into this point that's pointing over G. Right? That's the fibers.
Yeah, so I guess the other reason why this appears is because this that thing has H1. And so that H1 manifests itself as the derived structure on the, I guess, on the fiber. Yes.
As you know, please say this goes back to proportionally. You mean something like this goes back to even if there's no cycle, but makes on as well.
I mean, I was just thinking about crystals in general. I don't know if I can make a more precise evidence. Okay, moving on. So now the second big part of this talk. So I want to talk about the RAM space. And so I guess it's always good to know what the inputs of a construction would be and what its output. So it's a RAM space of something. We will be interested in the RAM space of X. For us, X is a curve, but a lot of what we say here is general. So, and I mean, it says there, right? It's there in the name, it's a space. And first approximation is that the RAM space, well, let's actually just, the RAM space of X is going to be the space of finite subsets of X. And because I probably forget to say it at some point, so every time I say finite in this context, I mean finite non-empty. Okay. So now, I mean, might as well dispense with the form with formalities. So let's get them out. So by so let me define this again formally. So that maps from a test scheme S to the RAM space of X are going to be finite subsets, again, finite non-empty. Subsets of maps from S, well, from S to X, there are from reduced part of S to X. So, I mean, I guess we can even try to draw some kind of a picture. I have to decide whether S will be vertical or horizontal. Let's maybe makes no sense for X to be vertical, S is horizontal. So we have okay. So there are finitely many graphs here, and technically the graphs only have to be defined up to infinitesimal thing. That's why the theorem. So basically, I mean, I want to say, for practical purposes, we're just talking about a finite subset of X, and here I'm trying to define what a family of finite subsets, over a base must look like. So that's yeah.
What do you mean by subset? I mean, is it the points of the
Yes, it's
Or-
yeah. I mean,
eight points,
the
or-
point is that because here everything is reduced, or rather this. So this is just a sum, and so I don't have to worry about any kind of groupoid structure or anything, right? So it's finitely many points. So a collection of maps with no multiplicity and no order. And that's the thing, that if we actually want to understand this object more, we want to have some kind of more hands-on understanding of Rand space, we can really think about like, okay, what's a finite subset of X? It's an n tuple of points where order or multiplicity does not matter. And so less formally, or I can consider various powers of X. So I can try to approximate the Rand space by looking at powers of X, where I guess because my set is non-empty and has to be greater than 0. So these are ordered n tuples of points of X. That doesn't give me a finite subset of X. And in fact, I can follow the definition and see that this gives me a map to the Rand space. But in fact, because when we think about subsets, the order of points and the multiplicity shouldn't matter. And what this boils down to is that I'm going to have a system of maps between those powers. So if you like, I'm going to have a map from xn to xm. And so for any surjective map from m to n, for any surjective map, and so examples of such things would be various kinds of diagonal maps, diagonals. And also you can have just permutation. These don't have to be order preserving. So diagonals and permutations. And these maps exactly somehow remove the difference between ordered sequences and subsets. So diagonals get rid of multiplicity, so to say, and permutations get rid of order. So if I consider, so I say that an interval of points, in an interval of points where you're allowed to apply this kind of reindexing is the same as a finite subset. And in fact, this has a precise statement. So I said it's less formally, but nonetheless there is a precise claim, namely that the rand space will appear as the inductive limit of this functions. Let's see.
Do you write X Durand there or?
Okay. So, I mean, for when we talk about subsets, somehow the fact that we don't care about multiplicity also means we don't care about infinitesimal transformation. So let's add how am I doing on time? Not so good. So now I think from a practical point of view, like I don't know if I have time for this example. So from a practical point of view, I really suggest kind of thinking about objects living on the rand space. So like because of this identification, we can think about objects living on the rand space as compatible systems of objects with connections on powers of X. And let's maybe let me just leave it as is for a moment in case there are questions. Okay. So I feel bad leaving it as is. So let me just say, for example, what in the first approximation, what, for example, a quasi-coherent sheaf on the rand space would look like. So somehow I want to say that you can understand a lot of things about rand space without I mean, it's good to know the precise definition, but somehow the calculations can be done in the following style. So what is a quasi-coherent sheaf on and I'm going to approach it from this point of view. So on the first level, so say the first approximation of this is that we should have a sheaf, again, quasi-coherent sheaf on X Durand, which is the same as a quasi-coherent sheaf on X with a connection if you want a D model. Sheaf with a connection. Okay, fine. Now, now I have to start with the D module, so otherwise we'll never get any. So, okay, what happens on the second step? On the second step, we now have X squared.
And one X.
Okay. Yes. So on the second step, we are going to have a same thing on x squared. So now we have a d module on x squared. But because of this various identifications, if you like, various connecting maps, this d module cannot be argued. First of all, we're on x squared, we're going to have a map commuting the two components. So x1, x2 goes to x2, x1, which means that our d module needs to be symmetric. So S2 equivalent. But we also have these two stories are not independent. So, and that's where multiplicity comes into play. We have a map from x to x squared, embedding it as a diagonal. So you have an embedding of x as a diagonal, and the restriction of your d module to the diagonal must be the thing that you had on the previous step. And so far, this seems relatively mild, not very scary. So what you should understand is that when we go to higher, like for example, when we go to higher powers, when we go to higher multiplicities, you will have many different ways to embed smaller powers to higher powers, and all of this. So all of the restrictions have to be the same. So, I mean, even in this case, there is a certain compatibility condition between these two structures, which might be obvious or not. If not, it's an exercise. Okay. Moving on. 10 minutes. And so now the last hero of the story, it's a friend space. So I want to so my goal is to define so let me first say what I should do, and then we'll see whether I do this or I don't. So my goal is to define the RAM version of the category of representations of my group G. So now representations G RAM. So, well, let me first write the formula and then say what I actually mean by this formula. So representation G RAM. So I mean it can be defined as quasi-coherent sheaf on. I mean, if I just do this, I would just get representations of G, and so it's not very surprising that somehow if I want to define a version of this, I use a version of that. But what is that version? So let me write this informally. So this parameterizes the following objects. First, I have a finite subset of my finite non-empty subset of X. So it's a N, and then I have a G local system on its formal neighborhood. It's formal. So I wrote this definition sort of in the point way instead of, so I guess points of a C rather than trying to say what it is for points of an arbitrary scheme. The definition is for arbitrary scheme is really similar. So, but I mean, what am I trying to say? So I have a curve X. I have a bunch of points. X. Let me do this kind of lift and index those points x1, x2, blah, 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 xn. And then I take formal neighborhoods of all of these points. So I'm going to have formal disks. And then I consider a G-local system on this union of formal disks. Well, the fact is that being a local system means that formal disk, because formal disk is contractible, or if you like, because the Durand stack doesn't fill the infinitesimal deformations, a local system on a formal disk is just basically a single, is determined by its fiber as a single point. So this is really a G, like it would be, if you have n points, it would be the same as just having a G bundle at a finite set. So now the things get interesting because exactly when we start varying things and when we start varying our finite subset in families, so somehow the way, so we have this mysterious rank space, for example, which you can try to approximate by things like this. And then we have an object sitting over a rank space, which over each individual point is very much understandable. It's just, I mean, this thing really looks like point mod g to the power n. But as the points approach each other, as for example, on this picture, as we approach the diagonal, then our two copies of G become a single copy of G. Yes.
Could you just define it with local systems on X instead of on D of X, on DX?
I mean, the whole point, right? So let me, I think now there can be a motivation to this. So the why did I suddenly start talking about this? What does the second part of the talk have to do with the first part of the talk? The first part of the talk was about local systems on X. But somehow the fact, I mean, it's local systems, but we study them global. We study them on X. Now, RAM space is our tool, our mechanism for studying objects locally. So the naive understanding of what it means to do things locally would mean you just take some kind of a neighborhood of a point, which in this story normally means formal neighborhood of a point. And that's, this is, you can prove some things this way, but it turns out that you can prove more if you realize that when two points collide, their formal neighborhoods sort of fuse together. And so RAM space appear all the time when we try to formalize, it's kind of the underlying base, underlying geometric base where this fusion happens. And in particular, this thing, we introduce this space as our, or maybe this space rather, as our local, or I don't know, RAM space local to global, however you want to call it, version of the space of local systems. So for example, if I have a local system, on X, then such a local system will give me compatible set of local systems on all of the little disks. So it will provide, if you like, a section of the map from this, a map from the RAM space back into this thing. So now I don't know if I answered your question or the question that I heard in my, and so
if here the formal neighborhood of point X is replaced by the point X little x.
Well, if you replace it by like local systems somehow, like if you talk about local systems, you want to be able to differentiate things. So that's why we don't. So I prefer to think about formal neighborhoods. And this is really important for N space, because if you just think about individual points and point 1 and point 2 collide, then you get point with multiplicity 2. But if you have a formal neighborhood of a point, that's like infinitesimal, that's like infinite neighborhood already, and infinite neighborhood here. They collide, you get a multiplicity infinity times 2, but that's still infinity. So, so this Rand space structure, it was, I should thank again for reminding me to include the Durham set here. It's really important for this Rand space machinery that we work with neighborhoods.
Sorry, what is RAM?
Ran is Ran X. Okay. There's only, so everything X is fixed once and for all. So what I'm saying, so RAM is that. I'm saying that this space parameterizes finite sets and local systems around these finite sets. But if I give you one local system on the entire X, this will generate local systems on all the finite sets. Yes.
Is X a fixed curve X here or an X a test C?
There shouldn't be any test scheme. So the test scheme is always S.
Okay.
X is always the curve. Yes.
So is this the base change of point over G to run S?
I mean, not quite, because when there are many points, you get many copies of G. So I think like the idea is to think about what happens, like what I realize I'm running out of time, and I am out of time. So so let me just say that so what happens in this case? Somehow the idea is that I want to have this kind of D module thing, and now I want to say the following. This D module will have an action of G, but not just an action of G. In fact, when we're away from the diagonal, I'm going to have two actions of G sort of indexed by the 2 points. So there is a D module on X squared with an action of G squared outside of the diagonal. But on the other hand, on the diagonal, I have only one copy of GX. And this action on the diagonal is compatible with the action off the diagonal via the diagonal embedding of G into G squared. Okay, let me maybe just make one sentence, and then I think in the lecture this will like why. I mean, I sort of explained why this thing appears, but what is the? I can also make this more precise. Like the reason why this category appears here is because objects here naturally make sense as tautological sheaves on the stack of local systems. So basically, I mean, and whenever you have a moduli space of something, this moduli space naturally has some kind of tautological object. In the case of local systems, if you think about things naively, these tautological objects would be parameterized by points of your curve. But if you actually think about higher versions of this, if you look at if you think about some combinations of these objects, you realize that they come from this kit. So I think I absolutely have to solve it.
Yeah, please feel free to ask Dima questions during the break.